I would like to emphasize that the purpose of this video and the Mpls video following this is to demonstrate my ability to configure network devices, and is for evaluation purposes only. I do not authorize anyone to use this information and will not be responsible for anybody using this information in these videos in their own network configurations, whether it be in a test or production environment. Thank you. I'm going to configure this network using an emulated software package called GNS3. I don't have the particular devices in my lab to be able to show you this in the real network, but this is the next best thing. Unfortunately, this is a bit of a small box, so as the configuration will progress, the performance will be degraded. It's just unfortunate. It's just a box I sort of picked up for $100 off eBay. So, you know, if this was Windows, I'm running it on Unix, because if I tried to run this on Windows, it would just die to death. So, yeah, you'll get an idea about how it looks anyway. So here's the software. And basically what I'm going to do to begin with is I'm going to create a core of 4 devices. So, and these will be a fully meshed network consisting of 4 P routers. For the purpose of this demonstration, I'll just call this one P1. So they're 7200 series routers. So basically I'm going to put 4 together. So, and they will be fully meshed, so that it's redundant and it's got multiple paths, and that will actually demonstrate the label switching quite well. Okay, there's 2961, so I'm going to be using for the PEs. I've just labelled them in this particular way so that it's easier to be able to see them. So it's so you'll be able to see exactly. I'll just label them 1 through to 7. So when they get connected up, you'll be able to see them easily. Now I've got all my switches now. I'm going to configure this 7200. So these are obviously got the out-the-box configuration from the software itself, which is not enough NVRAM to hold an image. So just going to increase that, and I'm going to put the slots in that I need to be able to connect to the other Ps. Don't forget, this is going to connect to all the other P routers, this particular one, plus the PE, which is PE7. So I'm going to need enough interfaces to be able to do that. So I've just put a couple of fast Ethernet slots in there, dual fast Ethernet slots. And the PEs, they're slightly different because they're different models. Again, though, we still need the same amount of NVRAM side to hold a fairly decent size image. And once again, I just need another slot with a dual Ethernet. So I just put the fast Ethernet in there as well. So what I'll do is, obviously I don't want to waste time just going through all these. I can just push these through pretty quickly myself. So I will just I'll just go ahead and do the configurations, and I'll come back and start re-recording again when they're all together. Okay, so here's the network completed. Obviously, like I said before, the P routers will be fully meshed, and the PE routers have a link to 2P, so there's full redundancy there. The IP addressing, the way that that's actually been configured is that the loopback addresses actually reflect the device themselves. So P1 will have 1.1.1.1, P2 will have 2.2.2.1, P5 has got 5.5.5.1, etc. The links themselves actually are just point-to-point networks. They're not actually configured in efficiently, but they're configured in the way so that you can identify them easily. So, like for instance, if I want to identify the between P1 and PE7, it's 192.1 for PE1, for P1, .7 for PE7, and then the 252 mask. So that way you can instantly identify the link depending on what routers that they're connected to. That makes it easy. It's not, like I said before, it's not efficient, but it does make it easy to identify the links for troubleshooting purposes later on. Okay, now I'll come out of the GUI and just use the user interface, because as you can see, this is only a Pentium P4 with 3 gigahertz of processor speed and 2 gigahertz of RAM. So I'm just going to run the emulation now from the command line. And in order to be able to get onto these devices now, because I don't have a GUI, I have to log in through the loopback addresses. So as you can see, as this emulator goes through, you'll be able to see that when it actually finishes, it takes a couple of seconds to just run up the configurations. Okay, so now I can list the devices that I've got there, and the console on the right hand side is 2000, so I can go to the local host and then just tell that. So I'll start the main router P1, so I just start it off, and then what I'll do is I'll just go to 2000, which is the console port for that one. So you can see it's in the process of starting, so I'll give that a couple of seconds to get up and running. If I try to do these, you can start them all at the same time, but it sort of slows down the machine quite a bit. So I just get the first one started, and it's on its way, and then I'll go and start the others in a bit of a sequence so that it doesn't kill all my processing power, and then I'll just push the rest off. So as you can see, I've started. So let me get the other one. So P3. So that's started. So. And now if I just go in the configuration, as you can see, I've put some stuff in there already, just to, for the links and stuff, and just got hosts so I can tell them from them inside each of the routers. Okay, so at this stage I'll just go into the configuration and take a look at the IP addresses. So as you can see that they're all up, and I'll start all the rest of the processes up, all the other routers up in the emulation. So that might take a second because obviously the process is a bit slow, so hopefully that'll be right. So as you can see, all the IP addressing is there on this particular router now. So and once all the other configurations will be up, all the interfaces should be there. So yeah, so I've got all the IP addressings the way that I want it to be. So and the loopback address obviously is as I want it to be in the documentation. So now all that's required is the routing protocols at this stage. As you can see, the only routing at the moment is via connected interfaces, so it's not seeing any other routes from anywhere else. So what I need to do now is I need to run a routing protocol. So the one I'm going to use is OSPF in this particular case. So what I'm going to do is just add the router configuration, routing protocol. I use router OSPF1 for every single one of the devices. Although the devices is independent, I can use any one I want. I'm going to use a router ID on each one of these just for purposes of identification, so that I can actually, if I need to troubleshoot, I can recognise which random process is actually running on route ID. So I'm going to add the loopback in. It's effectively a pretty straightforward, Class C sort of submask. And I'm going to add the networks in. Because the networks I'm using actually, all of them are actually begin with 192.1. I don't have any other networks because it's just one that actually connects to everyone else by its own .1. I'm going to use a mask because I've only got 7 devices, so it's only going to go from 1 to 7. So I'm going to use I'm going to sort of limit that subnet mask. So as you can see, so just makes it a bit smaller. I don't have to put in individual interfaces for each one of the points. So a little bit of a cheat here because I've already configured OSPF on all the other devices. So immediately I do this, so it's obviously going to actually pair up with all the others. So as you can see, it will start to actually build the OSPF adjacencies and put it into the database. So as you can see, P1 should have P2 as its neighbour, and should also have P7 as its neighbour, and P3 and P4. So those two you can see already. So it's started to appear with P2 and P7. So it should go, as it goes along, it should pick up the other ones as well. See, it's just picking up P3 now, and should pick up P4 at some stage. So as that goes through, that will pick all the other ones up. So obviously now P3 is now fully connected. So, and as you can see, 3 is a backup. So you can see that I've got designated routers and backup designated routers on these. I haven't got one because they're all in the same network, but they're all, each Ethernet interface is an individual network. So it will build adjacencies based on these individual networks. So there won't be, they will have their own designated router and backup designated router for each one of those links. As you can see, all the OSPF routes now are coming into play. So as you can see now, I've picked up the other one. So now I've got a full neighbour relationship with all the routers that I am neighbours with. Now, as you can see, I can we'll be able to connect on onto all the other routers, obviously because I've got that IP hosts in each of the routers. So I'm logging on to P2 now. So I'm just looking at the neighbours that P2 can see. As you can see, it's got a full neighbour list. It can see P1, P2, P4, P5. So it's got full adjacencies, full neighbour relationships with each one of those routers. So obviously P2 now is fully up and fully configured. So if I jump on PE6 now and take a look at its neighbourhood relationships, it's a little bit slower now because as it's starting to load up, obviously this is going to get the processor a little bit. So if I have a look at the OSPF neighbour relationships now, you can see that I'm neighbour relationships with P2 and P4, which it should be. The P2 and P4 though are backup designated routers, so I don't want that to be the case. I want the designated to be the core routers, so I'll change that around at some stage. I'll jump on to P5 and take a quick look at this one as well. So if I have a look at this processes, this neighbour relationships, again I am connected to 2 and 4, which is what I expect, and again it's set up as the cores being a backup designated router, so at some stage I'll correct that. So I'll just jump out of that one. I'll go through all the rest of them, obviously going to be exactly the same. So what I'll do, I'll just double check them and then we'll get back into the next stage. Okay, all the interfaces, all the devices are set up the way that I want them to. So now what I want to do is go ahead and actually configure the label tag component, I suppose, of Mpls. effectively, basically, you just need to go into each one of these interfaces, the interfaces that you actually want to participate in tag or label switching, and just use that command mpls IP. So I'm going to go across and do that on all these interfaces, because all these interfaces actually I want to participate, with the exception of the loopback, which I don't think you can do anyway on the loopbacks. So every interface will be participating. What this effectively does is make each device, or this particular one now, or the way it's configured, to be set up as an LER, label edge router, or a label switch router, OSR. The terms are interchangeable. People get confused about this, but a router can be an LER or an LSR, depending on where they are in the topology, and I'll explain that afterwards. So the MPLS router ID, I'm nailing the loopback to that. So, and I'll do that in the loopback 0 will be nailed to as the nailed address for all label distribution protocol. So a bit like the BGP, your source interface on BGP. Also, the loopback, these loopbacks will also be the nailed source for the BGP sessions as well, which will come later. So I'm just going to go to all the other routers now and do exactly the same thing. So I'll go through and run this command on all the other ones. So and then we'll come back to the video. Now, before I forget, first thing I want to do is actually change the priority on the core router so that they are the designated routers for their links to the PE routers. So I'm just going to go into the interface that's connected to the PE7 on this particular one and change the ISPI priority. And what that will do is that negotiations between those pair will make this particular router more important as far as OSPF is concerned, so that it becomes the designated router for that link. We're going to go across to P1 and do the same on this one. Right, so you see I'm on PE7 and I've just done a show IP ISPF neighbour, and you can still see that the neighbours are still backup directory routers. So I've just cleared the OSPF process on this router, and now you can see that the core routers are now the designated routers. So after this I will go across to the other two PEs and do exactly the same thing. But for now I'll just go and make a start on actually checking the MPLS. And so now in order to be able to do that, I'll actually go and have a look at the forwarding table. So which I can do by running the command show MPLS forwarding, or MPLS forwarding table. So when I get it right. So once this command's actually running, okay, so now what you see is a bunch of information. Probably the most important two parts of this is the local column, outgoing column. The local column in this regards, if we look at this particular column, it's any packet that's coming in that's got a label on it and it comes in will be switched. If it's a transit router, so the packet's going through, it will be switched with the value in the second column, and basically the third column is just the destination network that these tags are associated with, and the fourth one, which is pretty important, is whether the tag is switched or not and how many packets get switched. As you can see, there is no packets at all being switched here. And this is why the device is inferred as a label edge router or LER. A catastrophic change in the topology could change this, of course, so I'll be demonstrating this later. Another important note are the two entries in the second column marked as pop tagged and untagged. Pop tag means that the router is popping the label prior to delivering the packet. So the packet gets delivered to the next hop as a plain IP packet. For this particular entry in a router, it's known as the penultimate hop router for this network. So if we take the first entry for the network 1.1.1.0/24, for example, if PE7 receives a packet with a label of 16 on it, it will remove the tag, then forward the frame to P1. This saves P1 from having to pop the tag, then consult its routing table for the destination. Untagged entry simply means that the packet does not get labelled at all and just goes out as a plain old packet to this destination. The 143.3.3 example is an example of a packet that gets delivered without a label on it. So if I use destination 5.5.5.0/24 as an example, I can see that PE7 will add a label 25 and then send it via either two next hop destinations, routers P1 or P3. Using IPsec for this particular network, I can see that as well. It's imposing those labels on each one of those packets out of those destinations. In order for me to actually see though which path it's going to use, because obviously there's two paths it can use, either via, like I said, P1 or P3, I'll use the trace command to identify which way it's going to go. So the command to do this will be trace, because it's trace route, trace Mpls, and then IPv4, and then the destination network. It's got important to put the mask as well, it needs to be, and then I'll go through and see which way it's going. And in this particular case, I can see it's actually going by P3, and then it's going by P4, and then to get to its destination on P5, which is pretty optimal way to go. It could go either way, but it's obviously picked that route as the way to go through. So looking at this particular entry, as you can see that PE7 imposes a label 25, and then PE3 or P3 pops label 25 and then imposes the label 19, and then 4 pops label 19 and then sends it through to P5 unmolested. So if we so there you can see, if we go and jump onto one of the core routers, because obviously P7 we know that it's not doing any switching because it's a label edge router. So if I jump onto one that actually is switching, we'll be able to show you the actual switching in progress. So coming on here, like I said before, P4 will receive a label for 5.5.0 as label 19, and it should be popping the label. So if we're going to have a look, so as you can see here, and it receives a label 19 for this network, and it pops that label, sends it through, just as I said before. So it's yeah, so P4 is actually doing what it's supposed to do, and as you can see, it's actually switching those packets. As you can see in the fourth column, it's actually switching those packets. So this router is behaving as an LSR. Okay, now I'm on PE6, which will be regarded as an LER because it's on the edge. It's not part of the core, so it should be just not forwarding any packets at all or switching any packets at all. But I've noticed in this particular case that it has been switching packets on the 2.2.2 network, and it has actually been switching packets between 2.2.2.0 and 3.3.3.0 network. So you can see there hasn't been transiting packets for any other ones except for those two. I'm assuming that that's probably because when this all first started up, that maybe this was the optimal path through until the core finally got up and was established. That's what I'm making that assumption anyway. So what I'll do is I'll do an MPLS ping from P3, which I'm on here, and I'll send it back towards the 2 network to see if indeed PE6 is actually switching packets through this particular network. So I'll just fire up a number of pings, let's say 50 I suppose. So I'll just bang that through. As you can see, it's going through. So I'm just having a look. See, yeah, it's not incrementing. So I'm assuming that probably what it was because obviously this particular router started up before the others when I was starting them up, and probably that's the reason why it had that initial switching those packets. But you can quite clearly see now that the traffic is not going through PE6, so it's not transiting through there. And I can confirm this by actually going on to or taking a look at the forwarding table to see what happens with on P3 with the packets that are going to the 2.2.2.0 network. And as you can see, it's popping the label. So if it was going to go to 2.2.2.0/24 network via PE6, it wouldn't be popping a label. It would be putting a label, changing the label, and then pushing it towards PE6, which would itself pop the label. So that's the reason why I know this. So it's popping the label because the P2 is the last hop. So I'll jump in on PE7. So what I'm going to do here is I'm going to get a scenario where I'm going to get P7 to go to P5. So basically I'm going to send some traffic from P7 and it's going to go through to P5. And as we know from before, the packet that leaves P7 will go through P3 and then go through P4 and then end up in P5. So there'll be a tag imposed on P7, it'll be switched on P3, it will be popped on P4 and sent out to P5. So as you can see, and I'll move these around a little bit so that you can sort of take a look through there. So basically P6 has got nothing to do with this. So you can see now P6 has got for network 5, P6 is not switching any traffic. It's not going to it at all. It doesn't go anywhere near it. So what we want to do though is we want to make P6 become an LSR. So really we want some catastrophic event to happen, and that's going to be, the first one is going to be, well, P1's going to die for a start. So once we start disconnecting interfaces on the other routers, P1 is not going to be chosen as an alternate path. So now P1's dead. So the only route we've got is actually through P7, P3, P4. But we need to make sure that P2 doesn't come into the picture either. So we're going to need to make sure that the links from P3 to P2 are also down, and the links from P4 to P2 are down. So the way I'm going to do this is I'm going to start off by making sure that P7 sends a large ping to P5, and so that will be constantly running so that we can see when stuff starts going. So the next step is to actually disconnect the interface from P3 to P2. So we'll go to the interface, which is I'll log in first. So I'm going to disconnect the interface between P3 and P2. So I mean jumping on fast Ethernet 0/1 and then shut down that interface. Okay, so now any possible link from between P3 and P2 has been disestablished or stopped. So it won't make no difference to the ping because ping's going via P4. But if suddenly P4 had a problem, it would no longer try to go through P2. So now the next step will be to jump onto P4 and disconnect those interfaces between P2. And we need to disconnect the one between P5 obviously because that's where it's going to go naturally. So we disconnect those, which will then only allow a path through P3, P4 and P6. And because P6 is going to P2, it's actually going to be not popping it, it's going to be switching. So, and P2 will take the role of popping the tag instead of P4 like it is now. So I'm going to shut down the other interfaces. So we should be good, and we should still have a connection, hopefully. So now you can see, so you can see now that the it's being switched now. So P6 now is taking on the role of an LSR for that particular network. We lost a couple of packets on the way, obviously, because it had to recompute, obviously the routes, but not many. So yeah, so I'll continue to go through, and as you can see, it's imposing a tag rather than popping a tag. So now if we go back on a P3 and we bring back the interface between P3 and P2, so fast Ethernet 0/1, and we bring that back in, so it should instantaneously recompute that route, retag obviously that, because there's a more optimal route between P3 and P2 to get to P5. So if we now jump onto 6 and have a look at the tag switching for that, yeah, as you can see, it's no longer incrementing, so, and you can see that we haven't lost any traffic at all. So there's no increment now, it's stopped becoming an SO and gone back to its role as an LER. So if I clear the counters, clear the, not the counters, clear the counters for the Mpls. So clear the Mpls counters. So you should see that now, that would be 0, nothing going through it. So it's clear that, you know, it's doing the role we expect it to do. Okay, so in the next video, I suppose, I'll be going through the Mpls VPN